What up guys, welcome to Code Obsessed, and we'll be starting our next Leetcode Daily question, shortest path to get all keys. It's a Leetcode level hard question. I think it's a bit tricky, but we'll get into right into the depth of the question. So I'll give you a minute to just read the question. It's always better to read the question before actually watching the video, because sometimes there are things that you might understand if you read it yourself, okay? So yeah, I'll give you a minute and let's start, okay? So you're given an m cross n grid where dot means an empty cell, a hashtag means a wall, and at the rate means a starting point, okay? The lowercase letters represent keys and the uppercase letters represent locks. And we are specifically given in the question that you can only have 6 keys at a time, at maximum, okay? And we can move in 4 directions, up, down, left, and right, okay? And we have to return the lowest number of moves to acquire all keys. If it is impossible to acquire all keys, return -1. So there's a few things we came to know from the question, okay? I'll just write it here. 1, we only need keys. We only need keys. Okay, we don't care about locks unless there's a key behind about lock. So yeah, we don't really need to open a lock every single time, only if there's a key behind it. And second most important thing is that the question says we have to find the shortest path, okay, the lowest number of moves. And when we hear shortest, lowest, I think the first thought process should be BFS. Even without reading the question, your first thought should be BFS, okay? Now the question is why BFS and why not DFS, okay? Just imagine, okay, how DFS works. DFS goes through every single path, okay? Let's say this is a, for example, any tree graph, whatever, really, okay? And you have to find the shortest path to, let's say, this node from here. Okay, this is the root, and this is our destination, okay? And let's say this travels here. So what DFS will do, it will go here, it will go here, it will come back, it will go here, and then it will go here, and will find it. But it did not go through the shortest path, did it? It found the first path that was possibly the shortest path, but might just be the case that it was not the shortest path, okay? And if you look through all the paths and then find the shortest path, the time complexity is going to be fucked up, okay? So that's when BFS comes into play. BFS will find you paths at every single level, so you don't have to worry about it not being a shortest path. If you like find the endpoint, that is the shortest path. Simple as that, okay? So that's why whenever you hear shortest path, the first thing that should come to mind is a BFS algorithm. How does a normal BFS work? We keep track of the index that we are at, the I and j, since it's a grid, a 2D vector. So yeah, we keep track of the index. We keep track of a visited array, so we don't keep revisiting and go into an infinite loop. And we run the whole BFS till the queue is not empty. You know we use a queue every single time. It's a BFS, right? So yeah, we run it till the queue is not empty. So yeah, that's the basic thing. That's one thing you need to know, that for shortest path in the BFS. And second, we will need a little bit of knowledge of bit masking. Even if you do not understand, it's okay. You'll just continue the video and I'm sure you will understand it very easily. Okay. So yeah, going down to some test cases, let's look at the test case. This is the first case. This is the grid that we are given. Okay. And as you can see, at the rate means the starting point. So here we are starting. Okay. And we have to collect all the keys. So we can travel from here, get this key, go here, it's blocked, go down, get this, open the log, grab the second key. Okay. So basically, using a BFS first, okay, I'll just erase these things. So yeah, let's try to imagine the BFS algorithm. Okay, so the first move, this guy chooses to travel here and here. I'll just choose a different pen. So here, what the fuck? Yeah, so here and here. Yeah, that's where he chooses to go. And since he cannot go here, we'll go here. Then second part, since he's here, he can go here and here. Once again, cannot go, so he goes here. Now he's standing over here. He can go these two paths. Once again blocked, so he'll go here. Standing here, he can go these two paths. I mean, he can also go this and this path, but since it's out of bounds, I'm just not considering it straight up. So yeah, he can go here and here. From here, he can go 1, 2, 3. Behind him will be visited, so he won't go back. Cannot go here, cannot go here, cannot go here. Path ended. Then we go here. Then we can go to this, 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 and this. Once again, we go down. This is visited. This and this are blocked. Now we can go this side and this side. Now, if we go this side, we need to make sure we have a yellow key. the key that is corresponding to the log. Okay, we need to have a key. Only then we can go over here. So we need to make sure that is a condition in our code that keeps track of what keys we have. Okay, and then yeah, we go over here. We know we have this key, so we open this log, we travel here and get this key. So now both the keys have been achieved. So what will be the number of moves? Let's just think about the number of moves, guys. Okay, so we went from here to here: 1, 2, 3, 4, 5, 6, 7, 8, and that is the answer. 8 moves. Okay, just erase the whole thing so you can clearly see. And redraw the 8 moves. That's 1, 2, grab the key, 3, 4, 5, open the log, 6, 7, and 8. Grab the second key. 8 moves, our whole iteration is over. Okay. Now this similarly here, the person standing here, he can go up, out of bound, left, out of bound, down, out of bound, right. Oh, there's a lock, but we don't have the key, so he cannot go past this as well. Hence, we return -1. Okay. So this was the easy part of the question. Okay, just a normal BFS travel. But now, what's the typical part? Why is this question a hard level? Look at this test case. All right. So firstly, the start point can be anywhere. It's nowhere stated that first starting point and the number of, okay, it's not stated that the starting point has to be at 0 0, so it can be anywhere. So we need to find the starting point and number of keys, as we need the starting and ending condition of BFS. Okay, so yeah, we'll traverse to the array and we'll find, oh, this is the starting point and the number of keys are 2. Now just imagine how a BFS would work if we are just keeping track of the visited array. Okay, uh, we are at the starting point. Okay, we go over here, we see, oh, it's an empty space. We go over here, we grab this key. We have a choice to either go over here because this will be visited, so we can't go over here, or we can go over here. Okay, we either travel down or travel below. Okay, let's imagine down one. Okay, we come down, we can only travel down. Oh, it's a B lock, we cannot open the lock because we don't have the B key. So that ends that BFS part, and we go here. From here we can go here, and that's it. We cannot do anything. You see my point? Like, even if I grab this key, I am not able to open this lock. So what am I supposed to do? Let's not go into the code thing. Let's just go into the normal imagination, like what you are supposed to do. Okay, yeah, let me just redraw it. At red dot dot, it's an a dot dot. Okay, now if you are a guy, okay, like you are, imagine you are just someone walking. Okay, you are starting from here and you go here and then you go here and then you see, oh, there's a key. Okay, but now you want to know where the lock is, but since these were already visited, you cannot go back. But if you could go back, you'd go back to this point and see, oh, there's a lock over here. So now you're gonna think, oh, but how are we gonna know, right? If we do not keep the visited array, we'll go into an infinite loop. But if we keep a visited array, we cannot go back. Yep, that is the typical part of the question. We don't need to just keep the visited array, we need to keep a visited array with a condition. And what is that condition? That condition is, what keys do we have? Okay, if we get a key, our visited array is gonna be changed. Okay, for just imagine that if we get a key, our whole visited array is basically reset. We can go back anywhere. We can like basically just go back to the starting point once again, and we don't have to think. So we come from here, we go back to here. Oh, we found a key. Now these things that are visited are not visited anymore, because since we have found a key, we can always found a new route, which might have been logged earlier because we didn't have the key. Okay, I hope that made sense to you guys. So yep, that's the explanation, that if we put b instead of 04 normally, we would never be able to reach the B key, as after taking A key, we won't be able to go through the start again and open the A lock. Okay, give me 1 second, guys. So yeah, so that's why we need to keep track of the keys as well. So we'll use Bitmask and we'll just go right into the code and we'll look how we do that. Okay, so yeah, just normal N and M to keep track of the size of the grid, and then yeah, this is the amount of keys, number of keys, and our queue for the BFS will store the first index, the second index j, and the mask. Mask is gonna be which all keys we have. Okay, so I'll just give you a brief of how the mask thing is gonna work. Okay, we know there can be a maximum of 6 keys. Okay, so imagine you have a number 0 0 0 0 0 0 and 0 0 0. Okay, this number states that you have used none of the keys. Okay, this is A B C D E F. Okay, so or you can say just 0 1 2 3 4 5. So total 6 keys. Okay, uh, I'll just mark it the opposite way. A B C D E and F. Okay, so yeah, every time we grab a key, let's say we got A, we'll mark this as 1. We'll be like, oh yeah, we have A. Next time C, we got an E, so we'll mark this as 1. And this is how we keep track of what all keys we have. Now the bitmask thing only works because we have less amount of keys. Imagine we had maybe 100 keys possible, so you can't make a 100-bit number. That will be a 2 next to power 100, and that won't fit again. So since we have limited number of keys, you can think of using a bitmask to keep track of everything. All right. So continuing on, we have we'll just use the for loop. Okay, we'll use this for loop to know what's our start point, and how many keys we have, number of keys. Okay, so if is lower just tells you if it's a lowercase letter. So if it's is lower, we have a key plus plus. Else, if we find the @ symbol, we push in the start point into the queue. Yeah. So I have made 2 arrays, the dx and dy, since we can travel in 4 directions. This is just like simply basic way of you be like, you can just travel through these arrays and you will be able to travel the 4 directions. The 0 minus 1 simplifies the x part is -1. Okay, so this direction 1 0 is this, 0 minus 1 is this, 0 1 is this. So yeah, all 4 directions, that's is the way we'll travel. So we have a visited vector, a set, so we don't have to like worry about duplicates. So it will already all just keep track of duplicates for us, and there will only be unique number of elements. We start with int answer equal to 0, and yep, answer is gonna be the number of times the BFS runs, basically, because we have to tell us the number of steps, the minimum number of steps. Okay, so yeah, we'll simply start with a simple BFS while q not equal to empty, size equal to q dot size. For int I equal to 0, I less than size, I plus plus, we'll create a temporary vector which is q dot front, x is equals to the ith index, y is equal to jth index, and mask is equal to the mask. Okay, which in start is 0. Okay, if you remember, when we found the starting point at the rate, we initialize the queue with I, j, and 0. So mask at the start is a 0, or you can imagine it to be an infinite set of zeros basically. Okay, yeah, built-in popcorn tells us basically the amount of ones in this binary number. So yeah, we just put in the mask, tell you the amount of ones. If the number of ones equal to keys, that means we have picked up that amount of keys, and we'll just return the answer. Okay. Now we'll be traveling the 4 directions. K is equal to 0, k less than 4, k plus plus, and rho is equals to x plus dx of k. Simple things. And if they go out of bound conditions, less than 0, greater than equal to n, less than 0, greater than equal to m, or if we have a blockage, we'll just continue. Now int, we'll take a temporary variable int current mask and put it equal to mask, and if the character is greater than equal to a or z, so basically it's a small letter. Okay, we could have just used is lower, but yeah, if it's a lowercase letter between a and z, it means it's a key. And if we find a key, what do? We update our mask. How do we update our mask? That's simple. We do current mask is equal to current mask or one left shift character minus a. Okay, this might sound confusing, but it's not. Okay, just trust me. Just okay, we'll just try run this. Okay, what if we found an a? Our current mask is zeros. Okay, now we put or and one left shift character minus a. Now we'll break it up. Okay, what's a ch minus a? I'm waiting. Yeah, so it's gonna be what, 0. Okay, so one left shift 0, what is gonna give me? Gonna give me 0 0 0 0 0 1. Simple. We didn't left shift it by any means, right? Simple as that. and we OR this, 0 and 1 का OR होता है 1, otherwise it's going to be 0 0 0 0 0. See, we just got that we updated the mask so that we have used when. Now imagine we had D. Okay, so what do we do now? The current mask is 0 0 0 0 0 1, and now if character minus A, so D minus A is gonna give me what? B would be 1, C would be 2, D would be 3. So it's gonna give me a 3. So 1 left shift 3 is equal to 0 0 1 0 0. So it left shifted to the third position, and it's gonna be till here. I missed it by I left shifted by 2. So it's gonna be here, and now we OR both of these, and now we get 0 0 1 0 0 1, which signifies we have FED CBA. So we have A and we have a D. These are the two keys we have. Okay, so that's how the masking thing is working. It's very important to understand because you will use a bit mask a lot of times later on as well. So that's how you update your mask every single time you find a key. Okay, so this is our important step, updating the mask. And now we'll check if we already have it in the visited. Okay, if visited.find n row n call and current mask not equal to visitor.end, that means that set already has it. Okay, we already have it in the set, and we'll just continue, and then we'll go forward with if character greater than A or character less than Z, that means it's an uppercase letter. So it's an uppercase letter, which means it's a lock. If it's a lock, what do we do? Simple as that. We'll check if we have that key available. And how do we do that? Now that's the second part. Okay, now since you've done the first part, I think the second part is going to be pretty easy. Imagine we had 0 0 0 0 1 0 0 1. So we had the A key and the D key, right? And we using the mask to check if we have that key. Okay, so imagine we got a letter. Let's take A first, and then we're gonna take C. Okay, so we do mask and this time. Earlier we used an OR, and this time we're gonna use an and same thing. One left shift character minus A. So for an A, we're gonna have 0 0 0 0 0 0 0 1, right? This time we're gonna AND it. So only 1 and 1 will gonna give us 1, and everything else is gonna give us 0. So if this whole thing turned out to be 0, then I would know, oh, I don't have the key. But since it turned out to be 1, that means we have the key. Similarly, if I were to take a C, it will give me a 0 1 0 0. And if we AND these two, we'll get a huge 0. And since it's 0, that means we don't have the key. We don't have the key, simply. So if we don't have the key, we'll continue. We don't have to put the next index into the queue. Since we didn't have the key, we cannot go to that path. So if after all these things, we will straight away push the new n row n colon current mask into the queue, so we can do the BFS traversal on them again, and then once again same thing, visited of insert, right? And we'll insert that we have visited this queue, this index with this mask. Okay, so that's why keeping the track of the mask is very important. I hope you guys understood the whole solution, and we'll just update the answer simply, and we'll keep on running the BFS till this bit count is equal to the number of keys. If it happens, then the cool will return the answer, but if the queue becomes empty before we reach the answer, we'll simply return -1, because that's what the question said. If it's not possible, we'll return -1. So guys, that is the code. I'll go straight to Leetcode, and we'll run the code once so you can see that it's actually working. So yeah, click run, and it's running, and we'll click submit. Yeah, submitted. Okay, there you go. So that was the question. There are ways to improve it on the time complexity. You can make it a little bit faster, but that just complicates the question, and I don't think the interviewer is going to ask for anything more than this. Okay, so I think this is quite all right. If you guys understood, please make sure you like the video and comment down below. And if you need any help, or if you didn't understand anything, just comment that down below, and I'll make sure to help you guys out personally. Okay, thank you so much.